All right, I want to welcome everybody to our AI Futures Tech Talks. Today we're going to be talking about the biomechanics of motion. Before we let Jess take it away, first I want to talk to you guys about what the AI Futures program is for those who are new or joining us for the first time. Basically, our whole goal is to provide students or recent graduates with a way into a career with the DoD, these civilian careers. So we help match you up with jobs in your preferred area, preferred field, help you get those interviews. We also will do things like interview prep, your resume, go over your resume with you. And we also can help connect you with sponsorship opportunities for help with schooling or also internships. So if you need to get some extra skills before you're ready to go out into the workplace, we can help with that as well. We also, not only do we do these online tech talks, but we also do in-person events as well as sponsored events like hackathons. So there's tons of universities you can come and see us. Our next event that we're going to be at is, we were previously just at UGA Hack, so they're there right now. So we have some of our people from the AI Futures team on the call who are currently there. And this is in Athens, Georgia, so very exciting. And yeah, so if you want to schedule us, I'll put this back up at the end as well. Markham is great. He'll go over, what your background is, your current education, your graduation date, or if you've recently graduated, your goals, what you're looking for, and help you match you up with those jobs or internship opportunities. So from there, I'm going to let Jess take it away. I'll stop sharing my screen. Go for it, Jess.
Yeah, let me share my screen.
Oh, and sorry, one last thing. We have chat turned off. So if you would like to submit a question, we'll do Q&A at the end. It's under the activities tab, that little triangle, square, and circle, and you just hit QA, and then you'll be able to submit a question. All right, sorry, go ahead.
No worries. So everyone can see this and you can hear me just fine, right?
Yep.
Okay, sweet. So let's go ahead and get started. So thank you for that introduction. So I'm really excited to be here today. I'll go ahead and do this. Okay. So today I'll be talking about the biomechanics of motion. And just a little bit about myself. So I am Jessica Gilliam. I currently work for Mantle Technologies as a biomedical engineer. I received my bachelor's from the University of Dayton and my master's from Ohio State. I'm at the Mantle location here in Colorado. So this is where I grew up. This is where I'm from. So I love being here. So today we're going to kind of talk about background information of biomechanics. What is it? How do you study it? A little bit about my thesis work that I did at Ohio State for my master's degree. We'll kind of dive in the end a little bit about career path, as well as some industry R&D and like what are the differences between research as an academic and research as an industry professional. So biomechanics can be summed up as simply looking at how people move. So that's early steps as an infant to the use of a prosthetic. So you see the man has his lower limb prosthetic with a health professional helping him, learn how to walk and then run again. Contact forces and velocities and accelerations of an elite athlete, and all the way to how the body ages and the study of mobility and the appropriate use of a cane, for example. So biomechanics, in an engineering definition, is simply the kinetics and kinematics of segments in motion. So a good example is, how do distributed pressures and maximum vertical forces play a role in mobility and potential injuries? So a really great example is a study where female soccer players tore their ACL at much higher rates than male soccer players. So the key question here was, what is so different about the female anatomy that could cause this? Both teams, they're being trained in the same fashion, maybe have the same coach, the same weightlifting coach. They're wearing the same equipment, such as the same shoes, the same type of cleats, and they're playing on the same field, whether that be grass or turf. Yet there are key differences between the two groups. So really, what is the mechanism to an ACL tear? And the answer to this is that really there's excessive force on the ACL, and this is internally derived, whether it be by forces or moments. The ratio here of non-contact to contact ACL injuries is about 7-3. So 7 non-contact for every 3 contact ACL injuries, which is pretty interesting metric. The typical mechanism to injury is really this like rapid, awkward stop. And this is really in an anticipation of lateral movement. This makes a lot of sense though, right? Soccer is all about anticipating your opponent's moves. So the knee injury tends to be the victim of really this more proximal hip position and muscle activity. And these photos here, these are MRI scans of the knee. This is frontal, sagittal, and transverse planes. And this is a very typical layout for this type of injury. So there are several ways of classifying contributing mechanisms to injury, which can be intrinsic and extrinsic factors. Intrinsic just means that it's something you can't change, whereas extrinsic is something that could be improved or changed over time. So some intrinsic factors include alignment of your body, hyperextension or hypermobility, physiologic, rotary laxity, your ACL size plays a role, femoral notch size and shape, hormonal influences, huge difference between hormonal influences between male and female athletes, as well as your inherited skills and coordination. So all things that you were born with. And some extrinsic factors include strength, conditioning. What shoes do you choose to wear? Do they have a large sole on the bottom, or are they very thin? What type of spike are you wearing? A lot of turf players have plastic spikes, a lot of turf players have plastic spikes, and a lot of softball or baseball dirt field players have metal spikes. So what are the differences there? And then what is your attitude? Walking into the 6 a.m. workout that morning, do you have a good attitude? Do you have much motivation to be there? There can also be some combined factors here, which means that there's potential for improvement. This could include proprioception, neuromuscular firing patterns, or a skill increase. So like all injuries, there are key factors responsible for ACL tears, such as gender discrepancies in dynamic proximal movement. So while studies show anatomically there's a different hip width Q angle, when looking at the male and female hip types, this is not really universally valid because height and limb length, they also play a large role here. So it seems that really in development, the longer legged person or someone who's lanky, they have a greater ratio of lower to upper body segment lengths. And due to this, there's a natural moment arm, which gives them less ability to safely control that knee movement. So my graduate thesis work was not on ACL tears, but I did work with female softball athletes. I specifically took a look at stride characteristics and how these change in the execution of a softball pitch. In conjunction with this, I was looking at how the stride affects the forces and the torque seen at the shoulder. So basically, I was starting at the foot and working my way up to the shoulder. So why did I choose to study this? Why now? What prompted me to question the age-old, but softball should be better for the shoulder than baseball, right? So the simple answer is that I had shoulder pain. I played softball from the age of 7 till the age of 22, and I don't think my shoulder will ever be the same. I also knew and still know a number of women who pitched the same amount of time I did at elite levels and continue to have pain. So this really led me to question not only the mechanics of how I pitched, how I played the game, but the internal biomechanics of how my muscles, my bones, ligaments, and tendons are all working together. So a bit of background on the history of softball. So some researched injury information tells us that 73% of college pitchers have self-reported injury in a single season. So of these injuries, 44% were directly related to pitching. So out of all the positions on the field, the pitcher is presenting with an injury most often. It was shown in a study that conducted by Warner that velocities and forces and torques about the shoulder are similar to those seen in baseball. So still having an impact to the shoulder, just in a different rotational direction. And taking a look at repetition at the shoulder, around 37% of youth softball pitchers throw between 75 and 100 pitches per game. So now this is just per game. If you extrapolate this outward, there can be 2 to 4 games in a 2 to 3 day tournament play. And so this does not include pitching lessons or practicing on your own time or going to team practices and pitching bullpens. It doesn't include that. So really you're looking at a much larger spectrum of pitches being thrown per week, per month, and that load and what's being represented on the shoulder. So I knew there were a few other variables to consider during the study. So one of which was pitch type. So softball athletes usually have a series of pitches in their repertoire. This includes the basic 4 movement pitch types. That's the screw, that's the rise, curve, and the drop. So these are thrown in conjunction with the fastball. So looking at this image, we can see that each pitch is thrown to induce a directional change. Specifically, the ball is released with the spin type, of which the ball creates a flow field. And that boundary layer of air is forced to spin with the ball due to the viscous friction. So high enough spin rates can be obtained such that there's a full circulation around the ball. And this causes a side force. So therefore, those boundary layers will separate, and this will cause an increase of momentum on one side of the ball. And this is what's very well known as the Magnus effect. It's why softball pitchers are super big about what's their RPMs, their revolutions per minute. And so by achieving a higher spin rate, that RPM, the ball can generate a greater movement towards the pitch location. So for my thesis, I had 2 different purposes. The first is to investigate differences in stride characteristics and how these might change due to the type of pitch thrown. And second, to see if these alterations were associated with increased forces or torques at the shoulder. So is my stride changing when I'm throwing a fastball versus a drop or a curve? And at the same time, if I'm throwing a fastball, what does it look like in my shoulder? If I'm throwing a curve, what does it look like? So I hypothesized that movement pitch types would cause stride changes and that these changes would be associated with increased forces at the shoulder. So for my procedure, I went through a series of tests for each softball athlete. So this included a questionnaire, a manual muscle test, a functional mobility test, range of motion collection, and a full motion capture of their softball pitch. So I had each athlete take 2 different questionnaires. The first was a general demographic and activity information questionnaire. I wanted to know what sports they played other than softball. How often were they playing softball? How often were they going to pitching lessons? Are they playing 2 sports at the same time that I should know about? Things like that. I also took them through the Kerlan Jobe. This is an orthopedic clinic shoulder and elbow questionnaire. And this mainly was a pain assessment ranking of how their pitching arm and elbow was feeling. So making sure that we recorded any current or previous injuries prior to starting this study. We didn't want anyone coming in having some sort of previous injury or something that was bothering them, and then we're asking them to go through all these different motions and different pitches, and it might affect it. And it might also affect our study. So all good things to ask. So we did manual muscle testing as well. So this is a typical PT assessment of muscle strength. This helps us make sure that as a baseline, the muscles are firing appropriately. There weren't any pain reactions when opposing force was applied. This is really an essential test for determining movement impairments. The specific test used here is called the brake test. This follows the muscle length tension relationship and joint mechanics. Basically, an application of resistance is applied near the distal end of the segment, and this is where the muscle attached. So that's the perfect place to apply this and check out for all these things in case there's any pain or if they're actually not able to hold their muscle or their arm in place, then you know that the muscle isn't really firing correctly. Next, we performed a range of motion testing. The overhead athlete has really specific characteristics in the glenohumeral joint that should be noted. There's an excessive amount of external rotation and a decreased amount of internal rotation, and this is all measured from the 90 of abduction. So the decrease in IR, internal rotation, on the throwing shoulder has been referred to as GERD. This acronym is glenohumeral internal rotation deficit. It's seen in baseball, softball, tennis players, really just a physiological adaptation that is seen in any overhead motion sport. It's a loss of 20 degrees or more on the throwing shoulder, and this is in comparison to the non-throwing shoulder. So we're seeing this 20-degree loss in one shoulder compared to the other of one athlete. And these characteristics can be seen passive and active ranges of motion. So the parameters that were assessed in this study were included stride length, stride angle, stride foot angle, stride leg knee angle. Additional analysis was conducted on the shoulder to determine the shoulder joint force and moment. So as you can see here in this top image, this is Jenny Finch, and if there are any softball players listening to this presentation, you know exactly who this is. So this is her at stride foot contact, and you can see that front knee kind of begins to bend at foot contact a little bit. So this was an important point in the pitching motion. I was able to look at several other measures during the study just based on anatomical markers and their positioning. And so that first initial foot contact and that knee angle bend, so that was huge when looking back through and creating all the codes and doing all the data parsing for this study. So I've been throwing out kind of a number of terms so far. So let's take a step back. Let's take a look at the motion as a whole. So I've broken this up into 5 main phases. They're pretty typical to teach young athletes. If we take the arm motion and stick it on a clock face, we can tell the time. So that means that when the arm is at the beginning of the motion, it points down to 6 o'clock and cycles so on and so forth, 3 o'clock, 12 o'clock, 9. And that goes all the way through until ball release. So toe off, this is defined as the shift of the a shift of the back foot off of the force plate, or like the rubber mound, for example. So this is a key point that I labeled within my study. I had them on force plates, which I'll show in a minute. And this helped with creating a data marker so I could line up all of the data. And then our stride foot contact, this I defined as the initial force shown on the ending force plate. So defining when these happen, not only visually for the athlete, but also in a coded format, this was really helpful for pulling off all of accurate data. So just like, when you have physiological parameter data with timestamp entries for alignment, the same can be seen here, but with force specific triggers. So here's the lab at Ohio State. We used a Vicon motion capture system. This recorded at 300 hertz, synchronized ground reaction forces. I placed a net at pretty close range just to stop the ball from hitting anything. We had space limitations in this study, so it wasn't feasible to have a full pitching distance, which wasn't ideal for pitch accuracy verifications, but it was something we just had to work with. This was the space we had, so we had to use it. The athletes I worked with were between the ages of 13 and 19 years old. That's an important metric. 13, they're still learning some stuff. They don't have all of their pitches fully formed yet. And 19, I knew some girls from college, asked them to come in. So they're pitching at elite levels already. They have all of the pitches and more so in the repertoire. So it was a huge range of athletes. So we saw a bunch of different stuff. And so it was a limitation of getting that lower age group, 13, 14-year-olds, just because they didn't have some of the other pitch types. But the way we formatted this study, we had them pick what their favorite 2 movement pitches were. So for example, if I were to go in, I would say, okay, I have a fastball and I really like my curve and my drop. So that's what I would have thrown. And so we allowed them to pick their top 2 favorite. And that kind of eliminated some of that variability between the pitchers, just because even though the 13-year-old didn't have all of their pitches, at least they had 2 that were movement that they really liked. So that's how we did it. So the softball pitch itself varies between people in terms of stride lengths and widths. So that means that the size of our force plates, which they're the gray squares seen in that left part of the photo. These are not big enough to catch all of the stride variations. So I didn't want my pitchers to aim where they're landing or putting their front foot. This would pretty much mess up the entire study. So I built this mound. This was an old pitching rubber and turf that I had and I used when I was growing up. So I structured the setup out of 2 parts with like bolts, Velcro, very simple design. I laid it out so that each segment of the mound was only pushing down force on one of those force plates, so that we're able to get good data off of only one of the force plates if that's where the force is located. For this study, I used a full marker set. This is anatomical measurements and calculations. So you can see in these photos, I put markers on bony landmarks, as well as some mid-segment markers. They're offset from left to right. This just helps with going through and doing the data labeling, especially when the auto labeler kind of messes up a little bit. Additional markers were placed on their shoes and one on the ball to look at ball release and also at ball speed, which was actually really cool. And I'll show you a video of it in a minute. So for motion capture, we typically take 3 different snapshots of the athlete. The first is what is called the T-pose. This just verifies that we have all of the markers we need and that they all look like they're placed correctly. Second, we do a functional motion capture. This creates a simple motion set of all the markers. So here the participant is raising both knees, swinging the hips around as if using a hula hoop, and also moving the arms in 2 large circles, just creating marker paths that the camera has to pick up and then schedule out that for the individual. And then finally, the pitch sequence. So we asked them to pitch normally across the pitching mound, and the yellow marker shooting off the end is that marker on the ball. In these images, you can also see gray squares that the participant is standing on. These are the force plates, and the red arrows are just showing the equal and opposite applied force. So using all of that marker data, we can create a full musculoskeletal model in Visual 3D. So by importing this data, we can customize segments and create landmarks, and this will give us our final model file. So within Visual 3D, I was able to look at different trigger points, like I said before, that toe off, that stride foot contact. I was able to take a look at those key triggers so that I could then build my code off of that. All of that was very important so that we're able to see, okay, we're bringing in this data, we're parsing it correctly, we're calculating the right things. All of that is kind of like a check valve system. So looking at this model in Visual 3D, we looked at several different parameters. So we created these pipeline codes of kinematic equations. So for example, ground reaction force, we looked at the force plate, vertical force, z-axis, and extracted this data. And that ground reaction force was on the toe off, and that was also on stride foot contact. So this kind of lists out several of the parameters we were looked into. So knee flexion angle, the joint between the shank and the thigh, the joint angle between the shank and the thigh, excuse me, stride length, anatomical length between left and right ankle, stride angle, anatomical angle between left and right ankle, stride foot angle, anatomical angle between the toe and heel markers, the throwing shoulder joint force. So this was joint force at the dominant upper arm segment. This is at stride foot contact and at ball release. And throwing shoulder joint moment. So the joint moment at dominant upper arm segment, stride foot contact, and ball release as well. So here's what the model ended up looking like. I have joint centers and orientations and a modeled softball based on the ball marker. And in the video, you can see the coordinate planes in motion for the glenohumeral joint center. For the model axis, I had the anterior posterior direction as the Y, the medial lateral direction as the X, and that superior inferior direction as the Z. So this is what we kind of ended up seeing. So based on the model, the foot angle tended to be larger for the curveball. This means that when pitchers landed on their front foot, their foot is turned more outward than for the fastball. So this was very interesting because in some ways your foot is setting up the foundation for your knee, and your knee is setting up the foundation for your hip, and your hip is in motion and rotation during the pitch. So this leads to a few more questions, such as, does a larger foot angle put more strain on the knee? Are the hips in a higher rotation due to the foot placement? What if higher levels of rotation cause the chest and shoulder to move differently than other pitch types? All of these questions came up during this study, but of course they were not the goal of this study. So we then moved forward, looked at the shoulder. At the shoulder, we found that the joint forces were laterally higher for the fastball when compared to the curve, as well as anteriorly higher for the fastball when compared to the drop. So this idea that I had about movement pitches causing higher joint reaction forces was incorrect. It looked like the fastball was actually contributing to higher forces than these movement pitch types, which maybe leads us into different questions. Maybe this leads us into questions of, are pitchers slowing down so that they have a better RPM, revolution per minute on the ball? Are they slowing down so that they're able to do a forearm and wrist motion instead of snapping it through really hard on a fastball? So here are my hypotheses restated. So for the first, I said that movement pitches are thrown with alterations to stride characteristics relative to the fastball pitch. This was only found partially true for the ground reaction force and the foot angle on the curveball. And my second hypothesis was disproven, as it was shown that stride characteristics are not associated with higher forces or torques at the throwing shoulder. So shoulder pain, still a mystery, but one worth studying. Why is my shoulder in pain? I am not sure still. The motion capture tech that I used for my thesis is in some cases already outdated. There are markerless capture systems that can assess full body biomechanics, which is hugely impactful. So all of those hours of marker placing and labeling are replaced. But what about the time spent analyzing? So that's where this machine learning kind of enters the game, right? So human hours of data collection, modification, data parsing, all of this can be replaced by machine learning by just simply looking at the body, creating these markered segments in a markerless system, and then looking at that data, parsing that data, and learning from it. What is this athlete doing? How can it flag the system or flag the human component of, okay, I have analyzed this person's shoulder for a series of games and I'm seeing this, or this is happening and this is what's already pre-programmed as a red flag in the system. So this opens up all of these new avenues of development. So that was a bit about my thesis research. So we'll kind of switch gears a little bit. We'll transition into industry and what this looks like to do non-academic based research. So my experience in industry started in the Hulse Research Lab in Atlanta, Georgia. We were working with patients who had suffered a spinal cord injury and were going through a post-injury rehabilitation. I was a research engineer in the lab, so I worked with the XN suit system, and that's kind of on the left there. So this comprised of really a multi-IMU sensor system. This analyzed gait parameters. What's your stride length? What's your stride width? Knee angles, hip angles. What's the motion around the hips? I also worked with transcranial direct current stimulation. So this is also known as TDCS, and transcranial magnetic stimulation, TMS. So these are kind of interesting. They work similar. Like the way I like to describe this to people is you go to the gym and you do a bicep curl, 5 pounds, 10 pounds. You do it once a day for weeks at a time. It's the same thing, but with your brain, you're just strengthening those neural pathways. So I'm going in, I know that I have a foot spasm or something else, or a laxity. I'm going into the clinic, I'm getting TDCS performed, and I'm strength training that neural pathway of, okay, if we do TMS on the M3 quadrant, I know I'm going to be able to grip better in my right hand. And so things like that. So what I mainly worked on was this data analysis, like trend verification, huge data sets that I wrote codes for. So this was a really great experience for me. Even though I was already very proficient in code writing, I think that this bumped me up to like a whole new level, just because of just the magnitude of data that we were working with. I mean, this, you know, we're talking about at least a patient or two a day for weeks on end, and data collection, especially sample rate or frequency of data collection. We're talking really high rates. So that's just a huge data set that you're working with. But I kind of learned that this wasn't entirely what I wanted to do with my career. And I kind of find that the first job or two that you get into right after school, they won't be everything you thought it would. And, allowing yourself that freedom of moving around and finding a job that piques your interest is all part of, early career development. And so that kind of leads me to my current position as biomedical engineer at Mantle Technologies. So we're a small business, DoD contractor. So we work with a bunch of different military units of the government and work to solve problems that they are having. So I work with a really fun group of people. All of us have very unique backgrounds, which makes for some interesting ideas on how we solve these problems. So as a biomedical engineer, I work on all the physiological monitoring and performance enhancement programs. So as you can see, I have a dog running on a treadmill. This is just one aspect of my job. I look at these measures in both the human and canine space. We have a lot of customers that are within the special operation forces, which have canine units. So sometimes I get to come into work and play fetch, which is totally awesome. The dog running on the treadmill, his name is Gilliam. He is amazing. He's super cute, loves to play catch. And so here we're looking at some of his data. So these are some average force curves. This is looking at hind left, front right, hind right. This is the force that he's placing on each limb throughout his gait. Then we look below that. We're looking at paw pressure here, and we're looking at force, his average forces. So 105%, that's that front left paw. It seems like he's pushing that about 5% more than his front right, which it's not odd to have variations in gait, but just something to be aware of. And then we also have captures of step length, step stride ratio percentage. And then you can see the full the paw pressure map of the treadmill bottom right. So let's kind of go through a few high-level examples of, what do I do every day, my DoD projects that I'm working on right now. So first, we're looking at death prevention during a diving exam. So there are a number of challenges when diving, like deep sea diving, for example. This can cause an arterial gas embolism and cardiac arrest if not done properly. So we're tasked with the creation of a device that might alert nearby instructors of a diver's physiological state. So there are several things to keep in mind when trying to tackle a problem. Just like we have our own routine. So I like the way I like to wear my hair. How do you like to wear your hair when you go swimming? What wrist do you like to wear your watch on? Are you left or right-handed? The military has these specific standards on how they like to do things. So pitching a concept or idea that doesn't really fit this particular mold could cause a lack of support from our end users. So it's really important to not only figure out, okay, what's the problem? Okay, we have some diver deaths. We want to prevent arterial gas embolisms, but also, what do they like? What do they wear? What are they doing during these diving exams? And that is just one piece of that whole problem. A project that is currently our most advanced is the canine freeze-dried plasma. This is for rapid field use. So just like human plasma, this can be injected to reduce pain and increase return to action time. I have a background, obviously, in mechanical engineering, so I mainly rely on that knowledge to work on this project. I model all of the manufacturing process designs, so this could be an autofiller, a bag clamping mechanism, a bag opening device, a nozzle fitting mechanism. It really just depends on what stage of the manufacturing process is needed, what needs automation and improvement for this large quantity production, which is what we're really trying to push into. Another project we're working on is fatigue. So fatigue is a constant battle with our military. So usually a consequence of, operational hours not being met with sufficient sleep. So therefore, there are a number of neuro studies that we're working through to help increase sleep and alertness levels. This project has been fun to work with as it ties in very well with my previous experience and work in the Hulse Research Lab when I did TDCS and TMS. So that project has been a lot of fun. And then finally, we have our canines. So canines are an important part of operational support. We work with a number of canines for performance metrics, training, enhancements, drug therapies. These canines have a ton of energy. So you can see that in this series of photos of one of our very frequent visitors. So I work in a very fun, interactive, and innovative space. It allows our team of engineers to come up with solutions that haven't yet been thought of. As a small business, we have a small staff of engineers, which means that I really get the opportunity to have my hands in almost every project. This ranges from using CAD skills that I learned in my undergrad mechanical engineering studies to doing a significant amount of physiology research and sensor data analysis to working on paw pressures and analysis in the working canine. We also interface directly with our customers, so we get to see how it directly impacts and improves their lives or their canines' lives. So with that, I'll take any questions about previous work that I've done, graduate studies, current industry work. I have my email there and then also my LinkedIn.
Yeah, we've got some questions. So the first is, can we use biomechanics technology to benefit or support pilots and crew members in the aviation or aerospace industry? Is there a thing about biomechanics in aviation?
Sure. Yeah, I think that biomechanics can be applied to every aspect of our life, honestly. One of our studies right now is working with AFRL, the Air Force Research Labs, that's in Dayton, Ohio. And they're constantly doing research over there, and I'm sure that they have an extensive biomechanics unit as well. You can also kind of tie that back into occupational biomechanics. For example, a great study that was conducted like maybe 8 years ago was talking about people that load bags into airplanes and how different lift systems are utilized to prevent back injuries. And I'm sure similar things can be used for how do pilots sit in a chair and for long hours, like 8-10 hour flights and things like that.
Okay. Next question is, have you considered taking your analysis of a biomechanics movements in softball to a different repetitive sport like swimming?
No, that's a great suggestion. So that was my thesis that I did a little while ago now. But I kind of have taken the biomechanics from that and from from my first job from gait analysis into this canine space that we're working on right now. So that has been a lot of fun, but definitely biomechanics can be applied to any other sport or any other, human motion, really.
Next is, I might have missed this, but did you look into what other positions the pitchers played during your analysis? I caught and played outfield. What would be significantly different than if I caught and played third when analyzing shoulder biomechanics?
Wow, that's a really good question. So I did look at what all positions they played, just like I looked at the different types of sports that they played as well. And I would say your main difference, which you probably already sort of know this, is that if you played outfield versus third base, is your distance to throwing is much farther. So when we're trying to prevent someone from scoring and a ball was hit to the outfield, the distance you have to throw is much farther than a third baseman, for example. And that would create a higher force or higher torque on your shoulder.
All right. Next question is, what qualifications are common in the field of biomechanics R&D, i.e. motion capture, EMG, data science?
Yeah, so I would say background in IMUs, motion capture tech, EMG sensors, any sort of, like, for example, I first got into biomechanics. I had a really great undergraduate professor, and she really got me interested in biomechanics. Dr. Bigelow at the University of Dayton, she's awesome. She allowed me to just kind of help some of her grad students in the lab that was there. And so I would go to practice and I would come into the lab like 8, 9 p.m. and just kind of like help out where needed. Like maybe I was putting markers on a human body. Maybe I was just holding the camera, just small stuff, but it got me really interested in biomechanics. And it also allowed me to kind of put that on my resume too. It allowed me to say, hey, I do have some experience with motion capture, and I do have some experience with human subject testing because I was a part of some of those studies and I had to sign the IRB and other things to be there. So I think all of that can be really important in getting your foot in the door for biomechanics.
All right. Next question is, what college classes and experiences prepared you best for professional R&D?
Yeah, so R&D in the industry it's a trickster because you really need not only your mechanical engineering experience, depending on which section of R&D you're in, of course, but I mean, I'm relying on my mechanical engineering experience, my coding analysis, as well as like any electrical engineering classes I took. I'm kind of relying on all of that to create this R&D system or device. And of course, you're working with other engineers there with you and they're helping you, but all of those things are very important, at least for me in my current job.
Okay, and I know we are at time, so I don't know if you have a hard stop, Jess.
I don't. Yeah, I have probably another 5-10 minutes if
Okay.
we need.
Yeah, we've got a couple more questions. The next one is, can you go into detail on the day-to-day differences between academic R&D and industry R&D?
So I would say, I would reword that question. I would say academic research and industry research. Academic research, I find, and this is just a personal opinion, I find is much slower. Industry research goes much quicker. Academically, you are looking at all of the solutions. You're looking at what is like, oh, well, this might work, or this might be a solution to our problem. But what are the other things I'm not seeing? What are the other things? Am I asking the right questions? That's academic research. Industry-based research is, what is a solution, and let's run with it. What is a solution? We're hoping it'll work, we're running with it, and then you only readjust until something is not working. You're not trying to find every solution to a problem because you just really don't have time. So I would say that's the major difference.
Okay. Next question is, could we use biomechanics technology for Alzheimer's research?
That's a good question. I don't know. That's a really good question. I mean, definitely worth looking into.
Sure. Says, coming from a mechanical background, was it hard to pivot into biomechanics? What sort of new skills and subjects did you have to learn during the shift?
Yeah, so I really pivoted to biomedical and biomechanics in grad school, even though I had some previous experience from undergrad. It wasn't that difficult, honestly, because I chose my graduate program based off of whether the biomechanics and biomedical could be sectioned within the mechanical engineering department. So I thought that that was very important for me because I wanted to rely on that mechanical engineering experience. I didn't want to go straight into the medical field either. And so I feel like choosing a program that was specific towards that, and then also choosing jobs and careers in which I am still being used as a mechanical engineer but applying those biomedical principles that I learned in grad school.
The next question is actually for me. So it's asking if this presentation is going to be recorded and sent to us. So this is being recorded and it's going to be edited and uploaded to our YouTube, our AI Futures YouTube, along with all of our past Tech Talks as well. So you'll be able to review it there and go back and watch it again. So, yeah. And if you have any additional questions, you can always, Jess has her contact information there if you want to shoot her a question, or you can reach out to us as well at aifutures.us. So yeah. Are there any opportunities for people who have a BS in mechanical engineering to get into biomechanics R&D? If so, how can they tailor their resumes to get in?
That is a very good question. And I feel like the AI Futures team would be able to answer that very well. Markham's very good at receiving those calls about how to tailor resumes and things like that for entry-level jobs.
Yes. Does any team at your company look at the learning aspect of these complex motor skills, factors inhibiting or improving the motor learning?
Right now, none of our research is doing complex motor skills. We're doing like attentiveness and alertness systems neurologically, but we're not doing motor skills currently.
Next is, when I was working on a class research project for my biomechanics class, I was using OpenSim to look at the biomechanics of a gymnastics landing. Do you use simulation technologies like OpenSim before moving on to human subject testing?
Yeah, OpenSim is a great resource. That was just coming out when I was in grad school, so that would have been something that I would have looked at that first before doing human subject testing. They definitely have, and I haven't looked at it in a year or two now, but they definitely have a ton of different models uploaded already in OpenSim. If anyone's really interested in looking at biomechanics and how equations work and different stuff like that, I would definitely recommend that as a good resource.
And last one is, how did you assess whether the shift from softball pitch research to DoD research would be a beneficial career move? Was it scary?
Yes, it was scary. As every new change and adventure in your life will be, honestly. It was scary to go from elite athlete research to medical research. I went straight into spinal care research, and then that was scary to transition from there to DoD research because I wasn't sure, what that would look like. But I think if the job itself shows skills and different things that fit your resume and fit what you generally are good at, then I think that there's a great opportunity there and a great opportunity to research and do the things that you genuinely care about, which I'm very lucky with Mantle Technologies. I've been able to be on multiple proposal rounds now where I've been able to pitch different ideas that I would be really interested in learning more about and researching and creating for.
Awesome. Well, that's all the questions we have. I'm going to say thank you so much, Jessica.
Yeah,
this has been wonderful. I'm going to go ahead and throw up the contact information for Markham for those who missed it in the beginning. And there's a QR code. So you'll be able to see that and get that information. So if you want to schedule a call with Markham, that'd be wonderful. I'll hang on for a couple of minutes just so people can get that information. But thank you so much, Jess. It's been great.
Thank you, guys. This has been awesome.
Thanks.